Journal Club. So today, Dr. Nofal, our fellow, will be talking about corticothalamic network at ictal onset. And we'll be recording the session. I'll provide also a CME code during the presentation. Thanks all for joining.
Well, thank you, Dr. Mackey. So, as you said, I'm going to be talking about uncovering the spatiotemporal dynamics of the corticothalamic network at ictal onset. And this is a study by Panchavati et al., which was recently published in Epilepsy in April 2024. So, thalamic stimulation has shown promise in treating medically refractory epilepsy due to the thalamus's role as a central hub of the cortical network. And we know from animal and human studies using either neuroimaging or neurophysiology studies that there is evidence supporting the critical involvement of the thalamus in the generation, the maintenance, and in the termination of seizures. And we also know that DBS targeting the anterior nucleus of the thalamus has shown efficacy in reducing temporal or limbic seizures, suggesting a strong connection between the ANT and the temporal limbic system. We also know from other studies, especially in the Lennox-Gastaut patients and other patients, that the centromedian nucleus also may exhibit stronger connections to the frontal regions and other brain areas, thereby further supporting its potential as an effective target for the neuromodulation in non-temporal or extratemporal lobe epilepsy. Now, a few studies have investigated changes in the corticothalamic connectivity between thalamic nuclei and different seizure foci during seizures. There are some fMRI studies which offer good spatial resolution, but lack the temporal resolution that the EEG offers. Thereby, they're inadequate in elucidating the dynamic temporal changes in seizure networks. However, the EEG does provide this excellent temporal resolution, but the sampling signals from the thalamus sampling of signals from the thalamus is challenging unless clinically indicated because of the invasive nature of the sampling. So only those who undergo like phase 2 epilepsy surgery would be undergoing thalamic implantation of electrodes. Now, to enable personalized neuromodulation treatment, it is crucial to understand the distinct role of each thalamic nucleus during seizures, taking into account their anatomically specific seizure onsets. And understanding the dynamic changes of the corticothalamic network at ictal onset will help in optimizing the detection of seizures through the thalamic sampling with the RNS. So the more we know about the different thalamic nuclei and their networks, the corticothalamic networks, the more we're able to personalize or individualize each person's treatment, especially with RNFs. So the aims of the study were to investigate the dynamic connectivity changes within the corticothalamic network at ictal onset. And what they did is that they analyzed a unique cohort of patients with thalamic sampling during SEEG for thalamic neuromodulation. And they explored the intricate interactions between the seizure onset zone and two specific thalamic nuclei, the ANT and the CMT, across various seizure foci. So this was a retrospective study of patients with pediatric onset medically refractory epilepsy that was admitted to UCLA Children's Hospital, who underwent SEEG implantation between 2020 into the ANT or the CMT from 2020 to 2023. So ipsilateral ANT and CMT electrodes were placed to determine whether an ictal pattern could be detected in the thalamus. And if there were bilateral onset seizures, then bilateral thalamic SEEGs were inserted. And they found that more than 90% of their cases had active contact in or within 1 millimeter of the nucleus that was intended for. And they also reported that there was no complications after replacing the SEEG electrodes. And each seizure recording was time-locked to the seizure onset and 20 minutes of data before and after the seizure was used. So this is just a reconstruction, 3D reconstruction of the SEEG electrodes that were placed, as well as those that were placed in the cortex, as well as in the thalamus. And these are coronal views of the thalamic implants, the different thalamic implants that were thalamic regions that were sampled. And so what they used as analysis is a bit of a not a complex connectivity analysis. So using a bipolar montage, they segmented the stereo EEG into 4-second non-overlapping windows and calculated measures of connectivity. So they used 2 measures of connectivity, which I will briefly try to further define. So they used coherence, and the second method of connectivity analysis was the spectral Granger causality analysis. And what they do is that they take, so these measures are measured at baseline, 20 to 10 minutes before the seizure onset, and during the ictus or the seizure, 0 to 20 seconds after the visually marked EEG seizure onset. And the connectivity values were contrasted between the baseline and the ictal segment to determine the connectivity change. And they quantified this connectivity between the seizure onset and the anterior nucleus and the centromedian nucleus, and explored connections between different brain lobes for different seizure foci. And they also explored these connectivity changes across various frequencies, the delta, the theta, the beta, and the gamma frequencies. So what's coherence? What's this type of connectivity analysis? It's basically a measure of it's an indirect measure of synchronization and correlation between 2 time series signals at different frequencies. And this can range between 0 and 1, with 1 representing the highest degree of synchrony between 2 signals. It's usually used in EEG data analysis to understand the functional connectivity between different brain regions. So the average coherence values within each of the frequency bands, and then they average, these coherence values are averaged across the different electrode interactions. So let's say we have, for example, a coherence between electrodes in the thalamus and at seizure onset was averaged to obtain this value for thalamic onset interactions at a particular time window and a particular frequency band. So this is one type of connectivity analysis. We'll understand more after I show you the results regarding coherence and the Granger causality. The Granger causality is another measure of connectivity analysis. Connectivity, so it's just a statistical measure of how one time series influences another, and it can be bidirectional, where 2 signals can influence each other. It has also been used in prior studies for neural signal analysis, including EEG research, to capture functional connectivity between different brain regions. So let's go to the results. So it was a small sample size. They identified 10 patients with the thalamic electrodes, and they had these 10 patients had a total of 870 contacts, with around 80 contacts in the thalamus and the others in the non-thalamic regions. So 9 patients had unilateral SEEG sampling in either in the anterior nucleus or the centromedian thalamus, and only 1 patient had bilateral ANT coverage. And as you can see from the patient characteristics, so these are the 10 patients. There were different etiologies for their epilepsies, including unknown etiology, FCDs, Rasmussen, and even a patient with tuberous sclerosis. So heterogeneous population, which is also one of the limitations of the study, and with the various prior surgeries, including VNS, craniotomies, or resection surgeries. They are refractory, so on multiple anti-seizure medications, with different findings on MRI and PET scan. And from what we can see here, one second. Okay, so you can see the different thalamic contacts here on the right or the left, AN or CM. Most of the patients had implants in both the anterior nucleus and the centromedian nucleus. These are the other locations in the non-thalamic regions. These are the seizure onsets, whether it's frontal or temporal limbic onsets, and the type of seizures, whether they're focal motor seizures or non-motor or electrographic. So this is the first measure of connectivity, the coherence. And as you can see, there was a significant increase in the connectivity during seizures in all frequency bands in the anterior nucleus, except in the beta frequency band. And there was also an increase in the coherence change, which was the highest change was actually in the delta band, and in both the ANT and in the CNT. So the most change in the coherence, the highest percentage of change was in the delta band, 16.2% when compared to the gamma band, in both the anterior nucleus and as well as the CMT, 14.9% compared to 5.4% in the gamma band. Now, when you use the Gainger analysis, there was also a significant increase in the bidirectional connectivity during seizures. So what I want you to know about this, I know it's not an easy concept to grasp, is that the delta frequency was the major, the changes in delta frequencies were the major player in the connectivity between the thalamus and the cortical structures. And we'll explain more what this means in the discussion. And when you use this other type of connectivity measure, the Gainger analysis, there was also a significant increase in the bidirectional connectivity during seizures in all frequency bands, except the outflow in the alpha band and alpha and beta bands here. But also, similarly, the outflow of information was also most prominently observed in the delta band. Now, when there was also a statistical significant difference between the delta outflow when you compare it to the beta and gamma outflow in the centromedian, and between the delta outflow and the gamma outflow in the centromedian, and between the delta outflow and the beta and gamma outflow in the anterior nucleus of the thalamus. And
sorry, can I ask a question?
Sure.
When you say outflow, you're talking about, well, I mean, the Granger causality takes into consideration two different regions and to assess the source and the sink, doesn't it? Like where, so these calculations, they include cortical areas that have shown some directionality of rhythms with these thalamic nuclei. And if so, which cortical areas for each nucleus? Or did I not get it right?
Yeah, that's true. So the outflow between the thalamus and different cortical brain regions, but they did not here define which cortical regions they meant by. But from the discussion, I'm assuming that this was in the ANT, this was between the anterior nucleus of the thalamus and the temporal limbic structures. And for the CM, it was between the CM and the frontal structures. But they did not specify in the methods or in the results which cortical structures they were comparing to in terms of the bidirectional connectivity, which was, I thought, a bit weird. But from the discussion, as we will see, is that they will discuss this connectivity between the ANT and the temporal limbic structures and the CM and the frontal structures. And now from the on the bottom here of the panel, this is basically the latency, which indicates how soon after the seizure onset there was a significant increase occurs in either the outflow from the AN T or the CNT, inflow or outflow from the ANT and CNT. And as we can see here, that the latency increased as the frequency bands became faster. As you can see here in the gamma region, in both the ipsilateral AN and the ACN. So in frontal lobe seizures, the delta sorry, maybe Dr. Kubaysin, I think this is what you meant here. So sorry, yeah, this is part of the results section, where in frontal lobe seizures, the coherence showed a more pronounced increase at the centromedian rather than at the AN, 14.7 versus 8.3, and in limbic seizures, the delta coherence showed a more pronounced increase at the AN compared to the CN, 14.7 versus 7%. There was no difference between the CN versus the AN for parietal lobe seizures, and they did not do any kind of comparison for neocortical temporal seizures because they had a small sample size. So the inflow to the thalamus from the onsets increased mostly ipsilaterally during the seizures, which is expected, across the frequency band, but most prominently in slower frequencies. So delta, theta, alpha, mostly in delta range. And similarly, each brain's region's outflow from the thalamus was relatively limited also to the ipsilateral hemisphere, and also in slower frequency bands, so delta, theta, and alpha. So what they found is basically this is like a kind of a summary of their findings, so that the coherence between the seizure onset and thalamic nuclei significantly increased across all frequency bands, especially in slower frequencies. And in the danger causality analysis, there was also an increased information flow from the seizure onset region to the thalamus in all frequency bands. However, the outflow from the thalamus to the other brain regions was mainly in slower frequency bands. And there are some studies which show also the amplitude coupling between these slower theta frequencies from the thalamus and the faster frequency originating from the cortex. So prior studies had suggested that slow frequencies due to inhibitory long-range corticothalamic network may emerge early and be sustained during seizures. And also what the study provided is evidence of the bidirectional delta frequency that serves as a distinct marker of increased thalamocortical activity, which basically contains the inhibitory outflow from the thalamus to the seizure onset zone. And this also aligns with the traditional theory that the delta component of the 3 Hz spike wave discharges during absence seizures originates from the inhibitory corticothalamic inputs. Furthermore, these results underscore the significance of comprehending the spatiotemporal dynamics of the corticothalamic networks. So for frontal seizures, there was increase in the delta coherence in the CM compared to the anterior nucleus, while for limbic seizures, the coherence increase was greater in the anterior nucleus compared to the CM. And these findings align with prior other non-invasive structural and functional connectivity studies, which consistently demonstrated strong physiological thalamocortical connection between the frontal lobe and the CM and the limbic regions and the anterior nucleus of the thalamus. There was a recent study published on that investigated also an SEEG study that investigated the changes between the ictal connectivity during temporal seizures, and it had reported also increased connectivity between the temporal lobe and the anterior nucleus of the thalamus, and this is from the French, from the Bartholomé group. And basically, as you can see here, that at the onset of the temporal seizure, there is relatively rapid propagation to the ANT and then also to the pulvinar nucleus during temporal lobe seizure, during this example of a temporal lobe seizure and its propagation pattern, with heavy involvement of both the anterior nucleus of the thalamus and the pulvinar. And also the authors also in the study in our initial study, they further clarified that the delta frequency was the main outflow information from the thalamus to the seizure onset. And this is also the first study to provide evidence demonstrating the selective involvement of the centromedian nucleus over the anterior nucleus and frontal lobe seizures. So if you have frontal lobe epilepsy and you wanna target a target for neuromodulation, then this study argues that maybe CM stimulation would be favorable over the AM. This is another study that was published recently in Brain. It's a Chinese group with Dr. Worrell and Dr. Chauvel. And they discussed also the high frequency stimulation of the anterior nucleus of the thalamus, which was able to desynchronize the epileptic network in humans. So as you can see here, every time a stimulation is given, there was inhibition of the desynchronization of the epileptic network, and there was a decrease in the connectivity density whenever they stimulate the anterior nucleus of the thalamus. So the high frequency stimulation was basically of the more than 45 hertz of the anterior nucleus resulted in the desynchronization of the ipsilateral hippocampal activity and successfully reduced the seizure generation and propagation. So as you can see here, whenever they stimulated, also there was a decrease in the interictal discharges and in the high frequency oscillations in the hippocampus. So decrease in the pathologic discharges. We can also see in this study, we also know from the DBS studies involving the centromedian nucleus in Lennox-Gastaut patients that the CM was shown to be that stimulation of the centromedian nucleus was efficacious and decreased by half the number of the percentage of the median seizure frequency. And another connectivity study showed that specifically the parvocellular portion of the centromedian border is the optimal target for DBS and Lennox-Gastaut. So we also know that targeting the centromedian nucleus in patients with Lennox-Gastaut was helpful in reducing seizure frequency.
Just a quick, Omar, if you don't mind,
Yes.
clarification.
Yeah, sure, of course.
The Estelle trial on the right side of this slide, it showed statistically significant seizure reduction when 24-hour ambulatory EEG were done at certain intervals in the trial for the Lennox-Gastaut patients. However, if you look at the journal documented seizures, there was no statistically significant reduction.
Yeah, that's true. It was mostly electrographically, the electrographic seizures. So what are the limitations? Some of the limitations of the study is that it was restricted to the ANT and the CNT, so we don't have any information about what a pulvinar stimulation would do. But we know from other studies that ictal connectivity changes induced by the pulvinar stimulation in this study published in Brain Stimulation in 2021 correlated with improvement in awareness. And as I said from the previous study, pulvinar was also involved in the temporal limbic seizures, as well as in posterior quadrant epilepsy and the occipital lobe epilepsies. So this would be interesting to see what comes out of the connectivity analyses in the future regarding the pulvinar stimulation. And another limitation of this study was basically its small sample size and the heterogeneous etiology of the epilepsies, which might also have introduced variability in the network's underlying seizure onset and propagation. And thank you.
Thank you, Omar, for this presentation. I think there was a comment by Dr. Swartz that was addressed by Dr. Kubaisi in the chat. We can open the floor for discussion or any comments or questions.
Yeah, it's important to mention, Dr. Swartz, that this is my best shot at this topic with which I don't have firsthand experience. I just understand some basic mathematical principles of it.
Yeah. So regarding the methods of connectivity used, I mean, they were not very easy concepts to grasp the coherence analysis and the Gauge causality. And in the article, they just they mentioned briefly what each type of connectivity like measures, basically.
So if you want to reflect, I know you mentioned that, but if you want to
Yeah.
reflect again in a quick maybe comment clinically, how
Yeah.
would you? Yeah,
So
you
I
mentioned
think,
it, but if you can like kind of give another summary.
yeah, I think the most important thing out of this study is that if you want to consider like I think the clinical significance would be that for frontal lobe seizures, an appropriate target would be the centromedian nucleus, and for temporal or limbic seizures, then opting for a stimulation of the anterior nucleus of the thalamus would be favorable over the CMT, which is kind of which we knew from like previous studies, but also confirmed in this like connectivity study. I think these are the two main points, and the third main point is that the outflow, uh, of information from the thalamus is usually in the delta frequency range, and it can be coupled with the faster frequencies that are seen over the cortical surfaces. Yeah.
Thank you.
Sure.
And we have a question by Dr. Swartz about did they look at flow between the nuclei?
Between the anterior nucleus and the centromedium?
I believe that's what the question is, if Dr. Swartz can confirm. Yes.
They did not mention anything about like the internuclear connectivity between the centromedian and the anterior nucleus. No.
This is probably highly difficult to study because I would imagine that in the majority, if not all of these patients, only one nucleus was sampled during the SEG. Do they mention whether they sampled more than one?
Yeah.
In the
No,
same patient?
actually, in the majority, both nuclei were sampled.
Interesting.
Yeah, but
Well,
only in one patient only there was bilateral stimulation of the ANT, but all the others, I think, from what I understand here, is that both the anterior nucleus and the CM were stimulated.
If both nuclei were sampled in the same patient, you should probably reach out to the authors and tell them Dr. Swartz's suggestion to study the flow between the nuclei.
Yeah, that would be interesting also. Yeah.
So there's also a comment by Dr. Zempel that basically more centers are implanting the thalamus with SEEG, and we don't really know that the field yet knows the balance between safety and the value of information. Based on his experience at St. Louis, they have implanted when it might change the clinical decision of the site of the DBS, but it wasn't small number. He also conducted some surveys, but the field seems to have more centers implanted. Just wanted to read that comment.
Yeah. That part of why I presented this article is that we're also looking at our patients with thalamic implantation to see how we can study the thalamocortical networks. So this is part of my literature review. And from what I learned from this article is that it's not easy to study these kind of dynamics in the corticothalamic networks.
There is also by Dr. Swartz, a comment that there was a Stanford paper with an ANT and CM and pulvinar stem, and did confirm effectiveness of the ANT in limbic and CM in frontal and pulvinar and posterior epilepsies. I mean, it kind of goes, supports your summary slides, Omar, I would say.
Yeah.
Mhm.
Yeah. Okay, I'll take a look at it. Thank you.
Well, thank you, everyone. If we don't have more questions,